Hello everyone, welcome to my YouTube channel. I am Sabina Aydınova. In this video, I'm going to explain you this task. Using Cauchy-Riemann equations, determine whether the function exponential z is analytic or not. Exponential z means e to the power of z. Here z is complex number. Z is equal to x plus I times y. And e to the power of z can be written in this form, e to the power of x plus iv, and y is equal to exponential x e to the power of x times exponential iy e to the power of iy, and that's equal to e to the power of x times e to the power of iy is equal to cosine y plus I times sine y. That's also equal to e to the power of x times cosine y plus I times e to the power of x times sine y. In this case, this is real part of the exponential function, and this part is imaginary part of the exponential function e to the power of z. Let's show that Cauchy-Riemann equations conditions are satisfied or not. Cauchy-Riemann conditions, what are they? It is that let's say real part of the function is equal to function uxy, and imaginary part of the function, let's call it by function v of x and y. Then Riemann equations are du dx has to equal to dv dy, and du dy has to equal to negative dv dx. Yeah, du dx is the derivative of the function u with respect to x, and dv dy is derivative of the function v with respect to y, and du dy is equal to derivative of the function u with respect to u is equal to negative derivative of the function v with respect to x. This condition is called Cauchy-Riemann condition or Cauchy-Riemann equations. Let's show that this condition really satisfies or not. In this function, in this task, uxy is equal to e to the power of x times cosine y, vxy is equal to e to the power of x times sine y. Yeah. Let's find the derivative of function u with respect to x. Derivative of this function with respect to x will be equal to we find its derivative with respect to x. Cosine y, derivative of cosine y with respect to x is equal to 0, then the second term of it is equal to 0, then derivative of exponential x is equal to itself, then e to the power x times cosine y. We found derivative of function u with respect to x. Let's find derivative of function v with respect to y. Let's find it. Derivative of e to the power x times sine y plus with respect to y. Exponential x with respect to y, derivative of it is equal to 0, and derivative of sine y with respect to y will be cosine y. It is equal to e to the power x, yeah, I mean exponential x times cosine y. First condition is satisfied. Derivative of function u with respect to x is equal to derivative of function v with respect to y. It is explicitly seen that they are equal to each other. And let's find the second part of it. Derivative of function u with respect to y. Let's find it. In this case, with respect to y, exponential x with respect derivative of exponential x with respect to y is 0, and derivative of cosine y with respect to y is negative sine y, and then it will be exponential x times sine y. Let's find derivative of the function v with respect to x. E to the power x times sine y with respect to x is equal to derivative of function exponential x with respect to x is equal to itself, and derivative of sine y with respect to x is equal to 0. It's equal, then if this part is 0, only remain this part, it exponential x times sine y. It is clear that derivative of function u with respect to y is equal to negative derivative of function v with respect to x. If you multiply this by negative, then it's going to be this negative exponential x times sine y. It's proved that both these conditions satisfied. If it is satisfied, it means that this function analytic. If this Cauchy-Riemann equations condition satisfied, we say that this function exponential of z, e to the power of z, here z is a complex number, then it's proved that this is analytic function. Thank you very much for watching this video till the end. I might access this kind of mathematical videos on my YouTube channel. You can check them out. Please hit the like button and please support me, write comments to me, and please subscribe to my YouTube channel. Goodbye.